Hello, everyone. My name is Macarena Lagos. I'm currently an assistant professor at Universidad Andrés Bello in Chile, and I mostly work on testing cosmology with gravitational waves. And in this talk, I would like to tell you how we can use gravitational wave events with electromagnetic counterparts to perform a cosmological test of parity symmetry. So we're going to be thinking that there is a binary system of compact objects. We will focus either on black holes or neutron stars. And these gravitational waves, after they are emitted, they propagate for billions of years towards the observer. And in that propagation process, they prove cosmology, the expansion history, dark energy, dark matter. And that's what we want to focus on here, how the propagation of gravitational waves can prove a cosmological parity violation. So the propagation of gravitational waves on an expanding universe satisfies a very simple equation. It looks like a damped harmonic oscillator, as you can see here. Eta is the conformal time, k is the wave number, and hp is the gravitational wave that has two polarizations labeled by p, which can be left-handed or right-handed. And because the standard cosmological model is based on general relativity and it satisfies parity invariance, the predictions of the standard model is that both left and right-handed polarizations propagate exactly in the same way. This means that whatever amount of left and right-handed polarization was emitted, I should detect the same proportions because they decay equally, for example, with the luminosity distance and so on. So what actually determines the emitted polarizations and therefore the detected polarizations in the standard cosmological model? So here I'm going to be quantifying the proportion of left and right polarization by this ratio. And since I'm in Fourier space, this is a complex number that has some amplitude A and some phase phi. So if I have a binary system and it has a fixed binary plane, then it also has a fixed angular momentum vector L. So the observer, let's imagine that the observer is somewhere here located here at the top. So the line of sight would be given by this vertical axis. So there's two important angles that determine basically the relative location of the observer and the binary plane. Here, one is iota, is the inclination angle that you can see here determines the relative amplitude of left and right polarizations. It's really the angle between the line of sight and the angular momentum vector, L. And then there is additional polar angle, psi, which is this kind of rotational degree of freedom of L around the vertical line of sight here. And this is called the orientation angle. And as you can see here, it determines the relative phase of the left and right-handed polarizations. So why is this important? Because if my observations can tell me what are these angles, iota and psi, meaning what is like my relative observation angle of the binary system, then I can predict what is the detected polarization that I should expect in general relativity. And therefore, I can probe whether that agrees or not with the observations. Why is this important? Because if there is parity violation, then the relative amount of left and right-handed polarizations will change. So if we have parity violation, it's because the propagation of left and right-handed polarizations now has a modified equation that here I indicate by new blue terms. And if we have in parity violating theories, we showed in this paper that if there is parity violation, these modifications need to depend on odd powers of the angular moment of the wave number k. And because when I make parity transformations, I exchange left and right-handed polarizations, and I also have to flip or reflect the wave number vector k, then whenever you have odd powers of k in these modifications, then it means that there will be a flip of overall sign in these blue factors for the left-handed and the right-handed equations. So now here in a compact way, we're writing one equation for HP, but you have to imagine that there's two, one for left, one for right. And in the blue terms, one has a positive and the other one has a negative sign. So this is like generically what we would expect if there is cosmological parity violation that affects gravitational wave propagation. So from these equations, you can then write down the solution of what the observed polarizations should be. And for example, for the right-handed polarization, you have whatever you would expect in GR times these exponential corrections. And the important thing is that this first exponential is real and it comes from epsilon A. So this type of modification affects the amplitude of left and right, whereas this other modification that comes from epsilon V affects the phase. So it changes the relative phase of the polarizations, as you can see here, because these modifications come with a minus sign here and with a plus sign here. So these are relative changes. Now, these resulting waves are really integrated effects or integrated functions of these epsilon A's and epsilon V, as you can see here. So generally, you would expect them to grow with redshift or with cosmological propagation time. So let's continue characterizing this ratio of polarizations. So if I had parity violation in the cosmological propagation, then the relative observed left and right amount should be whatever I would expect in GR times this correction. Now, delta A is what people call amplitude birefringes. This is a well-known effect that is predicted by Trent-Simons theory, for example, and it dates back from as you can see here, from 1999. Delta V is what people call velocity birefringence. So this is less study. It can appear in Trent-Simons as a high order effect, or it can appear in other type of parity breaking theories as well. So here I'm going to be discussing how we can test both of these effects. So far, I've been super generic in terms of like the structure of these parity breaking terms, because we are trying to use a parameterized theory agnostic approach. But if we want to compare this with data, we do need to make specific assumptions. So the first thing that we are going to assume is that these modifications, delta A, delta V, are proportional with redshift, as you can see here. Because, as I previously said, these are integrated effects. So you, at least for low redshift, you could think of these as a leading order Taylor expansion. Now, these kappa A and kappa V terms are going to be the constant factors that I want to constrain. When these kappas are zero, I recover parity preserving cosmology. And if I find any evidence for non-zero values, then there is parity breaking. Now, what happens with the frequency, as you can see here? So remember that I said that in order to have parity breaking modifications, these epsilons that appear in the equation of motion need to have odd powers of k. So if you consider the lowest order effect, then you assume that they are linear in k, in which case delta A is also linear in k, and delta V is k independent because of the previous solutions that I showed you. So this is why as a function of frequency, you can think of this as delta A being frequency dependent, whereas delta V is frequency independent. So this explains this form here. Then H is just, the dimensionless Hubble factor and some factor normalizations factor of 3 or 2 or 100 Hertz. These are just normalizing my functions. So, okay, how would this effect look like in an actual signal? So in a gravitational wave signal from a binary system, the strain is the observable as a function of time. And in general relativity, this is like a mock situation. It would look like this in blue. Now, what happens is if on top of this, you add a amplitude birefringence during the cosmological propagation, then what you can see here is that there is some modification shown in black. And the important thing is that because amplitude by effringence is proportional to the frequency, then the modifications actually become more prominent here, which is associated to the merger of the binary system, because this is when the frequency is highest. And here in the early in spiral, the frequency is lower, so the modifications are more suppressed. So amplitude by effringence really induces a unique distortion that is not degenerate with any other general relativity parameter for these models, for these signals. And in particular, it's not degenerate with iota, with the angle that determines the amplitude of the polarizations left and right. So this means that with gravitational wave data alone, you can already constrain amplitude by effringence just by searching these unique distortions. So this is what was done by this group in 2023. So they consider 71 binary black hole systems, they stacked them, and they constrain this parameter kappa A. It is compatible with 0, and it is within 0.05. I think it was a 68 confidence level. And what we did is also consider an event that does have an electromagnetic counterpart to compare. And the only gravitational wave event so far with electromagnetic counterparts is the binary neutron star merger GW170817. So for this event, we did the same thing, kind of approach, but we are including the results and the constraints from the electromagnetic observations to get a constraint on kappa A of about 0.70. So here you can see that the constraint of this single binary neutron star is 10 times worse than the binary black hole constraints. And this is not only because of the number of events that we're comparing, but also because, and the most important reason is that this GW170817 event had a very low redshift of about 0.01, whereas binary black holes can be detectable up to much higher redshift, close to even 1. And because, as you saw before, the effect of both amplitude and velocity by effringence grows with redshift. And that's why it's much easier to constrain amplitude by effringence with just higher redshift events. So we also mocked how well we could constrain this kappa A with future binary neutron star events that could have electromagnetic counterparts and be detectable with the next generation gravitation wave detector Cosmic Explorer. And we obtained about a 2 order of magnitude improvement on the constraining of this parameter. This parameter can then be translated into constraints of a specific modified gravity theories such as Chern-Simons. Now, what happens with velocity by effringence? So here it's important that we're doing the same exercise of showing the GR waveform and the one that does include velocity by effringence effect. And you see a phase shift, right? Because velocity by effringence changes the relative phase of left and right polarizations. But it turns out that this phase shift is actually degenerate because it is independent of frequency. It is fully degenerate with the general relativity parameter psi, the orientation angle. So now you have to imagine that you have some emitted angle psi that you ideally could try to constrain with an electromagnetic counterpart, and some detected angle psi, which is the bias one that you observe with your gravitation wave data. Now, by combining these two pieces of information, you can constrain kappa V. So far, this approach is the only one that we have, that we are aware of, to constrain velocity by effringence when it is frequency independent. There are other works cited here, for example, assuming velocity by effringence to be frequency dependent, and in that case, you don't need electromagnetic counterparts. But those should be considered to be higher order effects in modified gravity. So let's review a little bit the electromagnetic counterparts of binary neutron stars. So here's a simple simulation, but for the event GW170817, we observed a kilonova, gamma ray burst, and a GRB afterglow as well. And all this information was used to get a very precise sky location of the system, get a very precise redshift information, and also, importantly, to measure the angles iota and psi, which, remember again, then they fully constrain what is the polarization left and right that you should expect in general relativity. So the general idea is that you could follow up the motion of the front wave of the gamma ray burst that then becomes the GRB afterglow for a long time so that you can trace the direction of propagation of this jet, which in turn should then tell you what is the direction of propagation, what is the direction of the angular momentum vector L of the binary system, because those should be in the same direction as the jet. So by following up the jet, you reconstruct the direction of the vector L. And this is what is shown here. You could follow up, for example, with radio observations for 100 or 200 days after the merger and like look in the sky where the electromagnetic radio emission is coming from. And then you constrain, for example, the orientation angle of this binary system. With additional modeling of the jet, then you could also constrain, as it was done previously in 2019, the inclination angle iota. So the electromagnetic information again helps you reconstruct these two special angles that in turn should tell you about the expected polarization. So this is about the polarization measurements from electromagnetic information. Now, what happens with the polarization measurements from gravitational wave data? So for the event GW170817, it was detected by two LIGO detectors, but it wasn't really detected by Virgo in Italy. So normally to get good constraints on the polarization, you do need a network of detectors with different kind of orientations to get constraints on psi. In this case, because it was only two LIGO detectors and not Virgo, the posterior distribution of psi is really flat, meaning that for this event, unfortunately, we had very good constraints on the electromagnetic observations of psi, but we didn't have good constraints on what is the gravitational wave observed angular psi. So because of this, really this event was unlucky and not really useful to constrain velocity by effringence, although it could have been if Virgo had really detected it. And this is why we decided to mock future binary neutron star events with electromagnetic counterparts again. So if we detected, for example, again, GW170817, but in the future with Cosmic Explorer and with two Cosmic Explorers, so you have like a network, then the posterior distribution of psi looks like this black line. It is always multi-picked because of some degeneracies, but you still get constraints on psi, for example, of around 0.04 radian precision. And on the electromagnetic side, you could get like 0.2 radian precision. These values really depend on the specific binary system. For example, what is the actual inclination angle? And this is why we compare also with another gravitational wave event that we call a representative one, that is further out in redshift compared to GW170817, and it's also more inclined, close to like 30 degrees inclination. And in that case, you get the red distribution, which is a little bit tighter. So this is a proof of principle that you could constrain in the future this velocity by effringence effect, for example, the kappa v parameter, to let's say about 5 radian precision, and then again translate this in the future to constraints on modified gravity. So because of the time, I'm going to leave you here with the summary slide. Thank you very much.